So, next part of chapter 9 is to remind you of the concept of the law of conservation of linear momentum. So you'll notice I have two carts. Both have these little springy things in the front, right? Right? And so what we're going to talk about is what happens when these two things collide with each other, okay? Now, I really can't show that very well here. This is so much easier to show in class, but here I can show, right? That's what's going to happen here. And so we're going to imagine it, but I just want you to see the physical, what it was that we were talking about. So if I have those two carts, and they're both the same mass, by the way, I'll call this mass 1. Mass 1 is initially going with some sort of initial velocity 1 towards mass 2, which is initially at rest. And they've got those springy things in between them, right? Which is going to be important for now. So what happens here? Well, when I have mass 1 collide into mass 2, what ends up happening here, actually this is a little awkward because the surface is uneven here, but we can see what happens there, right? Not a great demo, really. But what ends up happening is mass 1 ends up coming to rest, and mass 2 ends up moving in this direction, right? So there's the final velocity of mass 2. Now, mass 1 didn't have to come to rest. There's a whole bunch of things that could have happened to mass 1, right? If I showed you this interaction, I said, well, what are some of the things that could have happened to mass 1, right? So finally, there are really only a couple of things that could have occurred, right? One is that 1 stops and 2 moves to the right, okay? 1 could bounce back and 2 moves once again to the right. Another thing that could happen here is 1 continues right and 2 moves right. And the last thing that could happen, maybe if there was a piece of clay up here rather than the little springy thing, is 1 sticks to 2 and they move off together to the right. Okay, hold on a second. I'm filming for the next 20 minutes.
Oh, okay.
Okay. So those are the options of what could happen here. But notice, no matter what here, 2 moves off to the right. Okay. Well, why is that true? Well, let's talk about what's happening here, specifically in the interaction. So in this interaction, what's going to happen if we look at this instantaneously? When they're in contact with one another, and I'm not showing them in contact because I want to draw some stuff, that 1 is going to exert a force on 2. So this is the force of 1 on 2, which is the way we write that. And 2 will exert a force on 1. We know that there's a normal force on 1. There's a force of gravity on 1, force of gravity on 2, and there's a normal force on 2. We don't care about these because these are going to cancel each other out, right? The net force in the y direction is 0, just common sense in those cases. But what is happening here with these forces? Well, if we look at object 1 is moving forwards initially, but its net force is backwards. That means that object 1 is minimally going to slow down. But if that object slows down enough, it might stop. And if it accelerates enough, not only might it stop, if it accelerates enough, it might actually start speeding up while going to the left. Hence why you have these 3 situations that could happen. That would all depend on the size of this force and how long it accelerates for. But notice, no matter what happens, object 2 is going to accelerate to the right because there's only 1 force on it acting to the right, so that's the net force, meaning it's got to speed up while going to the right. Right? And that's got to happen here because there's nothing constraining the motion of object 2. Now, actually, there's nothing also constraining the motion of object 1, right? So we have a very interesting situation here. We have a situation here where we have an interaction between free objects. And what do I mean by free objects? I mean that these are objects where in the relevant dimension, the only forces that act are the Newton's third law interaction pair between the interaction objects. Right? In this case, the force of 1 on 2 and 2 on 1. Now we know, because it's Newton's third law, that from a vector sense, the force of 1 on 2 has to be equal in magnitude and opposite in direction to the force of 2 on 1. It's got to be true. That's what Newton's third law tells us, right? We're going to call these forces internal forces. So internal forces are always Newton's third law pair forces between two interacting objects. Now, if I had, for example, a car crashing up against a wall, though, right, we would have the force of 1 on 2 and 2 on 1, right? Still force of 2 on 1 when they collide and 1 on 2. But like car 1 is going to be affected a lot more than car 2. Well, why is that? Well, this wall here is not a free object. There's probably other forces holding this in place, that when this car exerts a force on this wall, there's like support structures, right? Some sort of support structure that are canceling out that force. So these would be considered external to the system. Why? Because if the system is called, or if we say the system is objects 1 and 2, this is not a force between 1 and 2. It's something else and object 2, right? Now, one might come back here and say, well, the normal force and the gravity force here are external, and you'd be correct to say that. But two things there. One, they're not along the relevant dimension, so I don't really care about them. And second, together they don't make a net force. And net forces are all that really count here. All right? So what we're going to have here is going back then to the impulse momentum theorem. So let's, right? And I'll write this in the non-calculusy way because it's just a little bit more convenient there. Notice here the impulse is equal to the net external force times average force times the time. Now, going back to here, the net external force on object 1 is this force. The net external force on object 2 is this, if I consider the system to be object 1 or object 2. And that makes sense because both of these objects change their momentum. But what happens instead of, rather than saying object 1 or object 2, I say the net external force, or excuse me, the impulse in the system is the net external force on the system, and this doesn't get a subscript because this is the time of interaction, right? In this case, when we have the collision between free objects, the net external force on the system goes to 0, right? Because there is no net external force on the system in the x direction here, because the only forces that are acting are internal to the system, the force of 1 on 2 and 2 on 1. And so that means that delta P sys is equal to 0. That would mean that if I have the final momentum of the system, well, let's actually put some vector signs over these things. The final momentum system vector minus the initial momentum of the system vector is equal to 0, or the initial momentum of the system vector is equal to the final momentum of the system. And that was true because the net external force on the system is equal to 0, average, right? This is our statement of the law of conservation of linear momentum, right? I'll put it in words then. The law of conservation of linear momentum. In the absence of net external forces acting on a system, linear momentum is conserved or constant through an interaction. And so that's really important because the law of conservation of linear momentum is really going to help us when we're talking about the interactions between objects, right? So really we've been dealing a lot with just one object, but here it gives us a better physics vocabulary for what happens when there are multiple objects. So let's look at a couple of problems. The first one we're going to do is 6, excuse me. And here we have 2 blocks of mass m and 3m are placed on a horizontal frictionless surface. A light spring is attached between the blocks or pushed together. A cord is initially holding is burned, right? So that would have been, another force on the system, but it's going away, right? So when we think about this, the only forces that matter is this spring pushing block 3m away and the spring pushing block m away. Or if you consider the spring just to be part of 3m, it is the force of 3m on m and m on 3m. We don't care about anything happening vertically here. We only care along the direction of motion, right? Now, later we'll do problems where we care what's happening both vertically and horizontally, but we're going to care about them separately because we always care about different dimensions separately. So what does this look like as a problem? Well, here we go. I'll model this for you. So it is really important that we have before and after pictures. Now I'm going to call them mass 1 and mass 2 because m and 3m is really kind of annoying, and we have this spring between them, right? And so this is mass m1 is m, m2 is 3m. We know the initial velocity of object 1 is 0, and the initial velocity of object 2 is 0. Before we get too far off the base here, I'm going to say that that's my positive x direction. I need directionality in every single one of these problems because we have vectors. And then finally, what do we have happening? Well, I have object 1 has a final velocity to the right, and object 2 is going to have a final velocity to the left, and that's going to be to the right. Boom. And that's what that looks like. What are we told here? We're told that VF2 is positive 2 meters per second. Okay, and we want to know what the speed of object 1 is. So how do we solve this problem? Well, the setup is simple. We say the initial momentum of the system is equal to the final momentum of the system because the net external average force on the system is equal to 0. Remember, that doesn't mean that object 1 is experiencing a net external force. It is. Object 2 is exerting a net external force, but as a system, they are not. And so what does that look like then? Well, just to be a little bit formal here, I'll say the initial momentum of the system is composed of the initial momentum of object 1 plus the initial momentum of object 2 is equal to the final momentum of object 1 plus the final momentum of object 2. Now we know that both of these zero out because initially these objects are not moving. Boom. And then here, well, object 1 has a mass of m, and VF1 is what I'm looking for, plus, and this has a mass of 3m, and then I'm told this is a positive 2 meters per second. They actually say a speed of 2 meters per second, but I'm going to say positive because I've made to the right positive because we care about velocities in this, because remember, vector, 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 okay? So if I solve this, we would find out that MVF1, or rather VF1, is going to equal 6 meters per second, and it's going to be negative, and that should make sense because we know just physically it's going to go to the left, but our answer tells us it's going to go to the left. So that's the A part of that problem. It says find the initial elastic energy of the spring given the mass. Well, what they're implying here is that energy is conserved through this interaction, okay? So if I think about this, that the energy initially is equal to the energy finally, well, is that true? Well, that's only true if the work non-conservative is equal to 0. Well, what forces are acting here? Or rather, more importantly, what forces are doing work? Well, the only force doing work here is the spring force. Spring force, that's a conservative force. So since the only force doing work here is a conservative force, energy is conserved in this case. So here we have both energy and momentum conserved in this very specific case. So initially I have spring potential energy, right? And then finally I have the kinetic energy of object 1 finally plus the kinetic energy of object 2 finally. And all we want to know is that. So this is 1/2 mass 1 v1f squared plus 1/2 mass 2 v2f squared. So 1/2 0.35 kilograms times, and this is the speed, so I'm just not even putting in the negative sign because we're dealing with non-vectors here, 3 times 0.35 kilograms, and we know this is 2 meters per second quantity squared. And we can throw that in our calculator then and solve. So that is 36 times 0.35 times 0.5. So the first term there is 6.3 joules, and then plus 4 times 3 times 0.135 divided by 2, and this is 2.1 joules. So together, that must be 8.4 joules is how much spring potential energy there was prior to this interaction, right? And so we're going to be seeing these problems that sometimes energy is conserved, sometimes energy is not. Now, I know it said I'm going to do 16, but I'm not. I'm going to do 17 because it is a better problem for what I'm talking about here. So we have a bullet, a 10-gram bullet, we're going to call that mass 1, is fired into a stationary block of wood. So I know that that is VI1. Here's object 2. That's my before picture. And then the bullet stops inside the block, right? So that's on some sort of ground. So the bullet is embedded in the block, and together these are moving off at some speed. So I'll call that BF of, say, both finally. Right? So the first thing I'm going to do after I draw my before and after picture is I'm going to say to the right is positive. Then I'm going to write down my knowns. I want my before and after picture, and I want my declaration before writing down my knowns. M1 is 0.01 kilogram. M2 is 5 kilograms. I don't know. I'm looking for this, VI1. I know VF of both things finally is 0.6 meters per second. So here, is linear momentum conserved? Well, very clearly, the force of 1 on 2 and 2 on 1 exists, right? The bullet's embedding into the block. The block is slowing down the bullet as it's embedding. There's nowhere the force is acting unless there's friction on this ground. We're told that there is no friction here. And even if there was friction, the collision force between the bullet and the block is going to be so much more significant than the friction force between the block and the ground that instantaneously, through this very narrow window of time in which the bullet is embedding in the block, friction's irrelevant. And it's not really going to, like if the net force on 2 is 6,000 newtons to the right, then does it matter that there's a kinetic friction force of like 0.8 newtons? No, it doesn't, right? So we're gonna use a lot of common sense, just like shortcuts in this, saying like, let's pretend friction is insignificant during the interaction, stuff like that. Okay, so the initial momentum of the system is equal to the final momentum of the system because the net external force on the system is equal to 0, right? That's true, 1 on 2, 2 on 1, no other forces are relevant. So I would say the initial momentum of object 1. Now, I could do a term for the initial momentum of object 2 here if I wanted to, but it's not going anywhere. Now, finally, I'm not going to have 2 separate terms here because these things have combined into one thing. So I'm just going to say the final momentum of both, right? And that's what we want to do. We want to construct our conservation of momentum equation based on the number of things that are moving. Now, I'm just going to zero that out in this step here. And now in this next step, I can just plug in. So I've got 0.01 kilograms times VI1, that's what I'm looking for, is equal to the mass here is going to be 5 kilograms plus 0.01 kilograms. And I know this is the final velocity of positive 0.6 meters per second. Now, I know you might say you don't need that positive sign, but it's good to have just to assert that I've very clearly shown that I've considered it as a vector, because where it matters, it really matters. So there we go. We can just do a little math here and find out, oh my, that bullet was moving at 3,000 5.06 meters per second to the right prior to this interaction, right? Which is pretty, actually, did I get that right? I may not have 5.01 times 6. Oh, I did. Good, right? So it's pretty brisk. So yeah, there we go. Now, if I want to know the forces acting here, I really couldn't do that. Why? I'd have to know the amount of time it takes the bullet to come to rest in the block to know the time of that interaction. But that would be pretty short. So if given that time, I could find something else. So there we go. I can find then what's going on. Now, just to show you, is energy conserved here? Well, let's actually look. If I look at the kinetic energy initially here, that would be 1/2 mass 1 VI1 squared, or 1/2 0.01 kilograms times 3,006 meters per second. So squared times 0.01, 5. And that gives me 45,180 joules, give or take some joules. Kinetic energy, finally, 1/2, and this would be both the things, M1 plus M2, V final both squared, or 1/2 5.01 kilograms times 0.6 meters per second. I think you can clearly see just numerically that there's no way that's going to be the same number, right? In fact, it's drastically less. It's not 0.9 joules, right? So a lot of that energy seems to have gone away. So energy is not conserved here. Well, why? Well, energy is only conserved if the work done by non-conservative forces is 0. The force of 1 on 2 and 2 on 1, that's a non-conservative force. That's an applied force or a normal force, however you want to think about it. That's not one of our conservative forces. So what is this non-conservative force doing in this case? What is the meaning of this work? Well, here energy is not conserved because that bullet is being deformed. I don't know if you've ever seen a bullet after it's been shot at something. That thing is just absolutely deformed. Its shape has changed dramatically. The bullet has embedded itself in the block. The block's shape has changed dramatically, right? And then when a bullet hits that, not only get to that deformation, but you have that sound and you have heat given off. All these things go into the fact that during this collision, energy is not conserved. This, folks, is going to be called an inelastic collision. An inelastic collision is one in which there is permanent shape change that occurs through the collision. Permanent shape change. Inelastic, non-elastic. Elastic means that things return to their original shape. So what is this interaction we had before? Well, it wasn't really a collision. This would be something that we would call an explosion or a recoil reaction. And these ones, depending on what is doing the explosion or the recoil, energy may or may not be conserved. Here, because it was a spring and springs exert conservative forces, we had a situation where this was conserved. But if this was like gunpowder in between there, then that's not going to be a conservative force, and therefore the energy would not be conserved in that interaction. So it kind of really depends on the situation. So for conservation of momentum, it only matters whether the forces are internal or external to the system, whether they're between the members of the system or not between the members of the system. Energy, all that matters is the nature of the forces. Are those forces conservative or non-conservative? It's two different conditions. So with that being said, I've modeled some problems with you and got you on a start with the difference between different types of collisions and explosions. And finally, what we'll do is elastic collisions. But Mr. Egan will take care of that.